Very nice. Uh, we will continue with the properties of Brownian motion. And last time we discussed that Brownian motion have a positive probability to concentrate along any continuous curve. Let us formulate again this statement and prove it. So we consider one-dimensional Brownian motion. Wt t belongs to the time interval 0, 1. We know that W has a continuous trajectories, so one can consider W as a random element in space C0, 1. This is a space of continuous functions. I will suppose that we consider only functions which start from 0, equipped with the uniform norm. This uniform norm is a maximum on the interval 0, 1 of a module of f. It is well known that this is a good separable space, and now W is a random element here, so we can discuss probabilities with which this random element lies in a different subsets of this space. Which subset will be interesting for us? Namely, we will consider the open modules in this space. We will take some f from C0, 1, and for positive R, we will consider such a set. This is a ball with the center in F and radius R, which is such a functions J from C0, 1, that the norm of F minus J infinity is less than. This is maybe one of the simplest set which arise when we began to study metric spaces. But for us, it is interesting what it is now in our space. Consider a graph of the function f, center of our ball, and maybe it can look like this. This is the function f. Then one can organize a cube around of f. This is a cube where the size of this cube is r. Yeah. And the ball consists of such functions f which lives inside of this corridor. Now let us formulate the last statement from the previous lecture. The following lemma holds. For every such an open ball, Fr, the probability that trajectory of W belong to this ball is positive. This is our statement. So let me recall again, because this picture is very important for future considerations, that it does not depend on the choice of our f. Only it is important that it starts from 0. You remember C0, 0, 1. So here can be our f. And also it does not depend on the size of the corridor. But whenever you have such a corridor along the trajectory of f, then probability that you will have a Wiener trajectory inside of the corridor is positive. Okay. Now let's prove it. I just recall you the following fact. We remember that C0, 0, 1 with the uniform distance is a separate space. It means that there exists a counted dense family of elements here. Actually, usually people use as such a family polynomials with rational coefficients, for example. Polygonal lines which have vertices at the rational type and rational value. So one can just recall analysis from the first year of education and find countable family, which is dense here. Next step. Due to separability, if I take the positive number r over 3, this r, I just divided it by 3, it remains to be positive. Then there exists a countable family, let me denote it by xn, such that our space C0, 0, 1 is represented as a union of the balls Okay. This is exactly which we said, that we have countable dense family. So for any point of our space C01, one can find the element from this countable family which is closer than this R over 3. Due to this, one can have the following relation. Now, let me recall you. The W is a continuous function. So, the probability that W belongs to C01 is 1. Here we have such a representation. It follows from there that at least one ball must have positive probability. Because in opposite case, if every such ball has a 0 probability, then the union also will be of 0 probability, because this is a counted union. So we understand now that at least one ball have a positive probability. So one can say that there exist. I will denote the center X star such that probability that W belongs to B X star R over 3 is positive. At least one ball exists. Now let's draw a formal picture where we will place two sets which we are discussing. One is the ball which we are investigating. So this is a ball BFR. And another one is this small ball B X star R over 3. But I will mark this ball because it has positive probability. We don't prove that this one has a positive probability. So now let's think what we can do. Let me recall you that we last time proved some interesting statement. We just proved that if we take function h, it is enough for us to take it from C01, 01. So it has continuous derivative that start from 0. And we consider a distribution of W plus H. Then this distribution is equivalent to the distribution of W, and even one can write density. You remember the density was like exponent of integral from 0 to 1 H prime dW minus 1/2 of integral from 0 to 1 H prime square ds. So what we can say that if we shift our function W, random function W on the function H, we get the distribution with the such density with respect to initial measure. From this point of view, one can say that for any such function h, probability that W plus H belongs to this ball B X star R over 3 is positive. Yes, because you remember we had a density, and this density is positive on all space with probability 1. This exponent. Due to this, if this is positive, then this also must be positive. But this is equivalent. Just do some geometry. Here I shifted W, but it is the same that I will shift our ball. It means that probability that W belongs to this ball X star minus H R over 3 is greater than 0. Yes. And it is true for any H which start from 0 and have continuous derivative. Now it is understandable that I can find such H that with this shift I can put this ball inside of our BFR. This is due to choice of the radius. Yeah. This is the shift minus H. Now everything became to be clear, because if the probability that W lies in this small ball is positive, then it is clear that probability that W lies in this big ball also is positive. So just let us mention that there exists such H that B X star minus H R3 is a subset of B F R. This is the end of our course. We proved that probability that our Wiener process will live in any corridor which we draw is positive. This lemma has very surprising consequence. Let me show you. This is a remark. Consider two-dimensional Brownian motion. W is a Brownian motion in R2. It means that W is of the form W1, W2, where W1 and W2 are independent standard one-dimensional Brownian motions. Now, let us consider two functions, F1 and F2, which belong to C0, 0, 1, such that if one consider gamma, this is just curve F1T, F2T, T belongs 0, 1. Then I will take F1 and F2 in such a way that gamma has the following form. Let me, for example, like this. Yeah? What is important for me, I just draw arbitrary smooth curve such that it has point of self-intersection. This one. Yeah. Then, now we can apply the previous lemma. I will apply this lemma to W1 and F1, W2 and F2, but I will draw a picture in R2. So I just draw a corridor, small corridor, along our curve gamma. Okay. And what we have from the previous lemma? From the previous lemma, we understand that this trajectory W T belongs to 0, 1, such a trajectory. One can say that such a random curve with positive probability will live in this corridor. I don't know its precise form. I just can say that it only lives with positive probability in this corridor. Now let us magnify this point and see what happened there. This is the magnification. This is our corridor. And now we understand that Wiener trajectory must came from here to here, and also it came from here to here. So it must definitely have points of self-intersection. We already proved very interesting and not easy to check statement. We proved that probability that there exists S which is smaller than T and from the interval 0, 1 such that WS is equal to WT is equal to is positive. Is positive. So we already proved that Wiener trajectory in two-dimensional case have self-intersections with positive probability. It is already surprising statement because before we even didn't know how to draw the picture of this chaotic Brownian motion. Maybe in this way, yeah? Why not? But it occurs that this picture is not true. It must have self-intersections. What is surprising that here exists much more stronger theorem, which was proved by 3 authors: Dorogovtsev, Erdős, Kaputani, and it was in the end of 50s of the previous year, like 58, that W has self-intersections of any multiplicity. Of any multiplicity with probability 1. With probability equal to 1. You see? So this is a very surprising statement. We already understand reasons why W have just double self-intersections. This topological reasons. We know that with positive probability W follow any continuous curve. But it occurs that with probability 1, it has self-intersections of any multiplicity. So it happens that trajectory of W have such behavior. For example, it crosses the same point 3 times, 4 times, 5 times, and so on, up to million. Yes. So it is a very surprising statement. From this point of view, it looks that geometry of the trajectories of the Wiener process or Brownian motion in the multidimensional space is very complicated and needs special tools in order to be investigated. We'll produce something, and let's start from the hidden probabilities for Brownian motion in different dimensions. So we will discuss now the following problem. We consider RD. We consider here Brownian motion, and we will ask for probability that there exists such t greater than 0, that Wt belongs to some ball, for example, X R. The picture is like following. We have some ball. This is X. This is R. And we start from 0 by our Brownian motion, and we begin to travel And we are asking, does it happen that it hit this ball, or it just go away and go? Yep. So let us discuss such kind of probability. Now, how we will do this? We will do this using some interesting generalization of the formula of total probability. What it will be? We will start from the following picture. Let this is a ball with the center at 0, and suppose that we start from here of Brownian motion. And maybe we will hit the boundary of the ball. This will be W at the hitting moment tau. Now we will discuss the distribution of W on this sphere. But before to discuss this, we have to understand that it happens that the Brownian motion will go to the boundary of the ball, will go to the our sphere. So let's prove this lemma. Such tau, which is equal of this t, the norm of W t is equal to R. R, this is a radius of the ball, is finite with probability 1 ratio. So, before to discuss the distribution of the Brownian motion when it hits boundary of the ball, we want to prove that it hits boundary of the ball with probability 1. And how can we prove this? The proof will be following. Let us discuss the following sequence of random vectors. So I take the differences of values of Brownian motion at the subsequent natural moments of the time. Then, due to the properties of Brownian motion, these are independent equally distributed random vectors, and each of these vectors have a normal distribution with a zero mean and identity covariance matrix. Due to this, it holds that probability that the norm of our vector is greater than 2r is positive, is constant, positive constant. You remember this random vector with such Gaussian vector with such parameters have a positive density. Due to this, we have a such statement. Now, let's recall that they are independent. So from Borel-Cantelli lemma, it follows now that probability that infinitely often is greater than 2r is equal to 1. Now it's understandable that we will go outside the ball definitely. Why? Because if we consider our ball and just start and put here W1, then W2, then W3, and so on, what will happen? That the subsequent distances, like this one, infinitely often bigger than the diameter of the ball. So we cannot stay outside all time. This is a proof. So we understand now that with probability 1, we will hit the boundary. Consequently, one can consider W tau, which belongs to S, this is a boundary of our ball. And one can discuss the distribution of W tau at this sphere. Let us denote by mu the distribution. Okay, then what happened? Let us consider how this measure, this probability measure, behaves under rotation of the sphere. Because we are discussing multidimensional case, so I will call rotation just any linear transformations with orthogonal matrix. Let U capital be orthogonal matrix. It means that U keeps the norm of the vectors. From other side, it can be algebraically expressed as follows. U star is equal U minus 1. And it is known that for all x from RD, U x has the same norm as x. So let us take such orthogonal matrix. And now I will check the new measure, new distribution, mu u minus 1. So this is an image of our measure under this rotation, generalized rotation u. So lemma is that it's again mu. So we see that the distribution of our Brownian motion when it hits the sphere from its center is invariant under rotation. Let's prove it. First of all, let me introduce new Brownian motion. U, it will be beta t, it is u of w. I said that this is new Brownian motion. We have to check this. How we will check? To understand this, it is enough to understand that this is Gaussian process, and it is true because its values are just linear transformations of the values of W. So it remains to be Gaussian, and it is enough to check its characteristics. The expectation of beta t will be equal to u because of linearity of the expectation on the expectation of w t, and this is 0. Now let us take the covariance of beta t beta s. This covariance matrix is equal to this is just usual calculus of what we did with the random vectors. Here covariance of wt ws, and here is u, which is equal to, you remember that w is a Brownian motion, so it is equal to t minima s multiplied by u star on the identity matrix on u minus on u, and you remember that u star, this is u in minus 1, so it looks like t minus s because of u is orthogonal matrix. So we understand that beta is a new Brownian motion. Now, note that if we define tau beta, this will be infimum of such t that the norm of beta t is equal to r. Again, due to orthogonality of our matrix U, it is exactly tau. It is exactly tau. Yeah. So it is the moment when our initial Brownian motion hits boundary. So one can check that mu is a distribution of, because of this is rotation, so this is a distribution of u from w tau, but it is exactly the distribution of u w at the moment tau. It is exactly the distribution of beta at moment tau beta. And because of this Brownian motion, this is a Brownian motion, then this is equals to mu. This is the end of the proof. You see, we showed that our distribution of the sphere is invariant under rotation. We already can guess what is this distribution, and maybe everybody expects that mu will be a uniform distribution on the sphere. It is true. Mu is a uniform distribution on the sphere. But we just write this conclusion. But I strongly insist that you have to think about this. This is not a simple statement. We just said we have a measure which is invariant under rotation. So it is uniform on the sphere. But you have to check, you have to prove this statement. And one of the possible proof is just to use characteristic functions. It is very easy. But you have to check this. So we understand that now we have uniform distribution on the sphere. Why I am considering this measure? Because if we want if we want to discuss the probability that if we start from somewhere, then we will hit some ball b x r. Then we can proceed as follows. Let us define a function of the initial point u. Let us consider starting point not only zero, but arbitrary outside of this point u. And let us define a function f of u. It will be a probability. I will put here u. It means we use already this notation. It means that we start from u. Probability that there exists t greater than 0 such that wt belongs to this bx. This will be a function of the starting point, initial starting point. Then one can get very interesting relationship relation on this function. How one can get it? Let us draw a ball with the center at the point u and a radius r. Then how it can happen that we will start from u and somehow get this ball bx. Naturally, before to do this, we must enter the boundary of this ball. Then we will have a point which we already denote by w tau, and then we must start from here and to hit those balls. Yes. So one can say that this is equal to just expectation of the. I just use a strong Markov property for w. So we first hit this one and occurs at the point w of tau, then we will go further. So this is expectation of probability w tau. And here is the same. There exists t greater than 0 such that wt belongs to this bx. So by this definition, we have that our function fu satisfies the following relationship. F of u is just expectation of f of w tau is equal to, you remember that we just proved that w tau has a uniform distribution on the sphere. This is integral with respect to s r, and here is f of v, and here is sigma r. So you see, for our probability that Wiener process or motion hit something, we get a very interesting relationship. Its value at any point is equal to average of its values along the sphere with the center at this point. And maybe you remember the time when you firstly face such relations. It was when we studied complex analysis, because this is a characteristic property of harmonic functions. And it follows from here that our probability is the harmonic functions, that Laplace operator of f is totally equal to 0. You see how interesting conclusion we did. We just were working with hidden probabilities for Brownian motion, but we get that these probabilities satisfy Laplace equation. So, what we are going to do now, we just will check what kind of the harmonic functions we can have depending on the dimension. Maybe you understand that depending on the dimension, we have different families of harmonic functions. For example, in dimension 1, one can describe all harmonic functions. It's just linear functions. In dimension 2 or bigger, the situation is much more complicated and the set of harmonic functions is much more rich. But we will still able to find our probabilities using harmonic analysis. This is a main conclusion of our lecture for today. Now, this is the end for today. Thank you for your attention.
Thank you, Professor. So, any question or comment, other students or teachers? Oh, okay, so thank you, Professor. So,
okay, see you next week.
Yeah, we will see you next week. Yeah. So have a good day.
Bye.
Bye.
Bye, you too.